In this example, we're going to perform finite element analysis to calculate the axial strain along a bar that's being loaded with an axial force. To get started though, we're going to do some back of the envelope or hand calculations to essentially predict what the answer should be before we perform the finite element analysis. And then if things are correct on both sides, we'll be able to verify that our simulation is in fact matching our hand calculations. So this problem involves a bar, and we're going to give it some cross-sectional area and also apply an axial force. Now, for this question, we want to resolve and give the resulting axial strain along the length of the bar. So that's going to be in the axial direction. It's going to be axial strain. And something to point out here is that unlike displacement, if we measure it, say, at the end of the bar, it's going to be different than, say, if we measured a local displacement here. But the strain is going to be the same along the entire length of the bar. So if we pick this location right here and we magnify it, and we have an element there, this could be a 3D element, but we're just doing it in 2D right now, we can figure out what the stress and the strain might be that are pulling apart this element. And it's going to be the same along the bar. For this type of problem, and actually any type of problem with an isotropic, linearly elastic material, we can write out what the strain in the x direction would be. And this is accounting for the idea that there could be stresses acting in orthogonal directions to x. So those being in the y and the z directions. Now, in our case, since we're only dealing with axial loading, we can see that the sigma y and the sigma z are equal to 0. So we're not going to be concerned with the contributions of, well, these zero stresses here, sigma y and sigma z, and a Poisson's ratio effect. We're going to just be able to say, let's use our old-fashioned maybe not old-fashioned, but our standard Hooke's law for uniaxial loading, where we have sigma equals E epsilon, and we see where that comes from. We have our sigma, and if we put the 1 over E over here, that's E epsilon x. So just like we see here, epsilon is going to be equal to sigma over E. The sigma we know is going to be the force divided by the cross-sectional area, so often we say P or A. In this case it would be, or sorry, often we say P or F. So it's P in this case, and epsilon is going to be equal to P over EA. And we can calculate that out by plugging in some numbers, as we see here. And this is the resulting value for the axial strain. So I actually haven't, let's go ahead and calculate this out. We'll use Google. Let's see here. What we get. So just go to Google. We have 1838 newtons divided by quantity 176 gigapascals times 1 centimeter. Go ahead and put in this like this, squared, and then that's all. Yep, that's in the denominator. So let's see what we get. All right, so we get 0.0001. Did it ask for it in microstrain? Yes. So we'll just go ahead and multiply by 1e6 to get it in a microstrain, and we get 105 microstrain. Okay. So when we run the finite element analysis, this is the value we're going to be looking for the axial strain. So how do we do the finite element analysis? We're going to use FreeCAD to create the geometry, and then use PrePoMax. So both of these pieces of software are open source and available to those who have PCs at least. Well, FreeCAD will work on both, but the PrePoMax is a Windows-based piece of software. So we open up FreeCAD, and we're going to create a new There we go. So we just click on new, and you can see I already had some bars from the past. Part, and we're going to come down to this part workbench, not the part design workbench, but just the part workbench. You can use part design to create your geometries, but it's for this type of geometry, I think it's simpler to just use the part workbench. So now we put in a cube, we click on this cube right here, and we can go ahead and change the length. What was the length? The length is 11 centimeters, and it's got a width and a height of 1 centimeter each. Okay, so 11 centimeters, so that's going to be 110 millimeters. Hit enter, and the width and the height are already set to 1 centimeter. I can scroll this around. Whoops. Yes, we can move it around. Good, like that. Okay, and that looks pretty good. That's our bar, and that's all we need to do in FreeCAD besides export this geometry. So we're going to export it to the STL format, and you can see, okay, I have a normal bar. Let's call this. This is session 8 Q1.stl. Okay, so do I get a dot in there? Yeah, now it's in there. Okay, go ahead and save it. And we're done with FreeCAD. So I'm going to close. Sure, if I want, actually I'll just discard it, but if I want, I can save it in the native FreeCAD format. So now let's do PrePoMax. So we need to go, I have PrePoMax in yes, I have it in a file system folder. So let's, okay, you can see some, I guess a bunch of my files. So we're using one of the developer versions here that's been extracted, and it's pretty recently downloaded, I guess beginning of the month. And I've extracted, and if you look at the notes from class, you'll see that how you can go about downloading and extracting it, but we're going to bypass that here and go ahead and run it. So I'm going to double click here on PrePoMax.exe and wait for the software to open up, and here we are. We are going to create a new model, and it's going to have, let's go ahead and meters, kilogram, second, degrees Celsius for units. It's going to be 3D. And we go back to file, and we can import that geometry. So here we go, session 8 Q1.stl. And as we discussed in class, this bar, let's see here, yeah, if we look at it on a scale, oops, it's not moving there. If we look at it on the scale bar, we see, yeah, it's about 110 meters long. Okay, well, how long is this supposed to be? It's only supposed to be 11 centimeters long. So we have a scaling issue, and this is common when you use STLs, that one piece of software will export it with one kind of set of units in mind, and then you open up another, and it doesn't, because it's unitless in the STL format. So what we're going to do is go to geometry part, and we're going to transform, and we're going to divide by 1,000 to get it down to, and we're going to scale by 1,000. So 0.001, like that, 0.001. Did I say 00? I said point, it should be 0.001, like that. Okay, and then we hit apply, and then it disappears. Well, that's because it's been shrunken by a factor of 1,000. If you come over here, you can do the zoom to fit, and here we are. Okay, so now this looks like it's about 0.11 meters. Let's see if I do this. I move it over here. Yeah, it's about 0.11. All right. Okay, and so now let's go ahead and start setting up our model to be able to perform our analysis. Remember that we are attempting to do this problem with an applied force here. And then we're going to measure the strain along the axis. Okay, so we've already got geometry, but what we haven't entered in the system are the elastic modulus, Poisson's ratio, and the load. So we'll proceed. Okay, so before we get to those points, if you don't add that information, right? You don't see much in this um, tree here. So we can go downward. There are multiple ways to do this, but let's just kind of work our way downward. So we're going to go into the mesh setup, and we had to discretize this box into a number of material elements. Okay, and so to do that, let's see. Oh, we don't want to just create. Okay, or yeah, I mean, I want to do the create setup. Okay, that's what I want. I don't want to create the mesh. So I guess if I do it here, you can do it either here or you can do it here. Let's try to do it here. So we're going to create the mesh setup. Good. Click on meshing parameters. We're going to do part. Click on part, and then click over here on the actual part. And then it's going to ask us for the maximum element size. So here, so now you might want to exercise a little bit of how do you say, judicious insight or judgment here. This is going to be, I know that 5.5 millimeters is going to be a little bit large for the small or for the max element size. So I'm actually going to bring it down to this case 2 millimeters. All right, we're going to hit OK. Okay, and then we come over here and we then do the create mesh, and we wait. And yeah, that's pretty good. Okay, so you can see it's only showing the kind of external portions of the elements, and it's done on all 6 sides of this object. But there is a mesh inside as well. Okay? So at this point, we're going to, if we move downward, I know something about this problem because, of course, I've done it before, and that I want to apply the force, say, coming out of this face over here. So I want it coming out. The way PrePoMax does things is it will, if I say, here's a force, it will assign it to all the nodes on this face. So the nodes are like all these vertices that have been created in the meshing process. I don't really want that. I just want to apply one force there and then have it pull on the whole face. So what I'm going to do is I'm going to define both a point at which I apply the load, and I'm going to define the surface that's essentially connecting all these nodes to each other. So what we can do is we'll go ahead and we'll create a surface, and we'll go ahead and we'll select this face right here. You can see that it kind of went orange, and now it's created it. It's called surface 1 right here. I hit OK. And then we're going to put a reference point on this surface. The easiest way I found to do that is, since I know the dimensions, is just to go ahead and put in where that coordinate, where I want that reference point to be with its coordinate. So it's going to be out at 0.011. No, sorry, it's 11 centimeters, so 0.11 meters. See, and now it's in this corner, you saw it jump, and I want to put it up. So this was a 1 centimeter by 1 centimeter, so I can do 5 millimeters. Whoops, okay, that's 5 centimeters. See, but it's nice that it shows. So another 0. 5 centimeters, or 5 millimeters, sorry. There, and now it's located at that location. Okay, so now I've created this reference point and I have the surface. In a little bit, I'll combine them to each other. But let's move down, or we'll tie them to each other. So let's go down a little bit, and we're going to define our materials. So, or our material. We're going to use an elastic material, so we can click on elastic, move it over. And here's an opportunity to put in the Young's modulus. We said for this problem that the Young's modulus was going to be 176 gigapascals. All right, so let's do that. And the Poisson ratio, oh, I got to look back, is 0.3. Okay, that's pretty standard. So let's go back, and that's not back. Here. Okay, so 176 gigapascals, so 176, and then I can type GPa, that's nice, and 0.3 for the Poisson's ratio, and I hit OK. Okay. Sections we are going to create a section. Actually, it's required. We're going to create a solid section, and this is by selecting the entire part. So I'm going to go to Part again and click on Part, and now that thing is solid, and I do OK, and it's called Solid Section. It won't run the simulation if you don't do this. There's going to be an opportunity here to create a rigid body, okay? This rigid body, and I said tie before, but we want a rigid body, okay, that is going to be linking between the reference point and that surface that we created, okay? So we're gonna, actually we're gonna use, so you see it already says reference point 1, right? You see reference point 1 is over here, so it already knows I want to use that reference point for my control point. The region, I don't have to select it. I can just put in, or I don't have to select it clicking. By clicking, I can put surface name here, and there's only one surface, surface 1. So now it's made that a rigid body, and they're connected to each other, okay? So that means that, well, what is a rigid body? A rigid body in this case is something that doesn't bend. It doesn't exhibit a deformation. So when we have, for example, the force in a minute being applied at this reference point, and that point is connected to a surface that's completely rigid, and that rigid body is connected to this face of this element, or face of this structure, okay, it's going to not bend, and it's going to evenly distribute that force over the entire area. Okay, so here we go. And now from this point, all right, we don't need to do anything here, but we do need to tell it what type of physics we're running. So in different finite element analysis, different simulation, numerical simulation software that does finite element or finite volume or different techniques, you often define what's called physics. In PrePoMax, it's called steps. So we're just going to create the physics that we want, and it's going to be a static step. Okay, you notice that all these things say step. So it's just like static physics is what we're doing. And we hit OK. Now a whole bunch of other options pop up. Here is a boundary condition. Well, for this, what we want to do is create a rigid boundary condition on this left end. So we're going to do create boundary condition. We're going to call it fixed. And I can't see it. Okay, but we'll move it over here. And we're going to do it to the surface. Okay, just like that. And that is going to be fixed. We hit OK. All right, and so then now that's what it looks like, and it's highlighted the whole thing, and it's rigid. So it's not going to go anywhere. We'll talk about some of its effects that we did in class already. For the load, we're going to create a concentrated force, and we're going to apply that at reference point 1. So we can go ahead and say reference point name, reference point 1, there's only one. And now we see F1, F2, F3. Well, the one direction is the X direction, the 2 direction is the Y direction, and the 3 direction is Z. So we have here, if we were to go back, you'd see that it's 1838 newtons, okay? And then F2 and F3 are 0. And so we hit OK, and it's good to see that this force is coming out of that face. You can change the direction or make it negative, right, if you want to have it be under compression, but this is a system that's under tension. Well, we've set up our model, and you're like, this took longer than just doing a simple calculation. Yes, it did. For simple geometries, it's often better to use your hand calcs, the physics, the analytics, the analytical techniques that we've been bringing up. But here, we can go ahead and we can do more complex geometries that you wouldn't be able to do by hand. Okay? But this is just a first example. So we see that it went ahead and solved. It only took it a few seconds. And we can click results here, like this. Okay, and now what do we see? We see, okay, that there's a new tab, or there maybe it wasn't completely, it might have been empty before, but anyway, if I went back in time, I'd know. So we have a geometry tab, which we already had, and we had the FE model, which we already had, and now we have this results tab. And this is kind of cool and colorful and exciting. With this geometry, and by the way, I just hit shift in the middle mouse button to be able to do that dragging. And then middle mouse button does this rotation. Okay, so what do we see here? We see that it's saying it's showing displacement all, units of meters, and it has this color bar right here. Okay, so if I click here, nothing happens because that's what it's showing currently. I might be interested in displacement in the x direction, right? Or I might be interested in displacement in the y direction, or I might be interested in displacement in the z direction. At any rate, this is the complete displacement. In U1, I mean, this is uniaxial loading. If we were to use flee or plee, right, we would hopefully get the same result that we have here, that this point is moving out 11.4 microns, okay? Now, what are we really interested in? We're not interested in stress for this problem, although it's probably good to check it, okay? It's looking uniform, and if I checked it, I had 1838, okay, divided by 1 centimeter squared. So that would be about 18.4 megapascals. Wait a second, but that doesn't, it's not showing that there. Why is it not showing it there? It's showing it something different. Well, there are some interesting behaviors happening, right, at these edges and at these faces that we have essentially made rigid, right? This is fixed, and this face is rigid. This is an elastic material with a Poisson's ratio, okay? So what does this mean? This means that as I pull in one direction, I'm going to get strain in the other directions. Remember, we said this with this equation right here, okay? That if you pull in one direction, the Poisson's ratio will give you strains in other directions, right? So if I had epsilon y, for example, then I would have equals, epsilon y would be 1 over e times quantity sigma y minus nu times quantity sigma x plus sigma z, all right? So here, yeah, the material model predicts that you're going to have some strain, okay, in the orthogonal directions, but these walls are saying, no, 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 you cannot move. You cannot do that. So when that happens, the material actually doesn't move here, but we have some stress being induced, okay, along these edges. So what are we going to do? Are we frustrated? Are we, this is not 18 megapascals or 18.4 megapascals. Let's go ahead and right-click, query, and we're going to click on, let's say, some point over here. All right, and what do we see? We see a value of 18.38 megapascals. That's, or 1.84 times 10 to the 7th pascals. That's beautiful. That's exactly what we're predicting, okay? So as we get far away from these rigid and fixed ends, we get to see the behavior that is more indicative of what we would expect. Now that we still haven't verified our problem here, okay? So the question was asking us to calculate the axial strain. This is axial stress. So now we go to strain, and we click on E11, so that's epsilon 11, all right? And we get a value of 0.0001044, okay? So if we were to move this over 6 decimal places, what would we have? We'd have 100, well, we would be in microstrain instead. And so it'd be 104.4 microstrain. And what do we calculate in here? 105. Okay, you're like, oh, we're off by 1 microstrain. We're off by less than 1%. We're off by maybe 0.5%. Okay, because this was 104.4, so that's like 0.6 over 105. Yeah, that's less than half of, that's oh, I guess that's about half of a percent. Okay, that's pretty good for finite element analysis. Now, which one of these answers is really correct? Well, they're both really close to each other. Okay, But if you're doing the analytical calculations like we did, or the hand calcs, right? Remember, we're thinking about averages, okay? And if you're doing the finite elements, right, we have a bunch of discretized elements in here. And we have edge effects, okay, or surface boundary effects. So either one of these is going to be more than acceptable for the types of problems that we're looking at, okay? And in general, when we think about safety factors, which we'll talk about in the future, we'll never prescribe just a safety factor of 1%, okay? You know, in aerospace, maybe you get to like safety factors of 17% or something like that. So in terms of our calculations matching our finite element analysis, I'm very satisfied here. And I hope you found this example helpful. One other thing I guess I should add is for the homework, if you're in the class, what I'd like you to do is to include, of course, well, I missed it. Hold on. What we want you to do is calculate this, include this answer, right? And so that, you can put in 104, 105, whatever you want to put in. I mean, not whatever, but the value that's close, and then it will auto grade that. And then we want you to upload a screenshot of what you've got here. So if I've got this right here, this is showing the strain that I want. I can do a screenshot just like this, and I can go ahead and I can save it as a JPEG on my computer, and that's what you'll go ahead and upload, all right, to the computer. So this is going to be axial strain or something in a bar, okay? And that's what we want. Highly suggest that you make sure that your model and your calculations agree completely before you hit enter, because Canvas will give you a new problem to solve. Okay, thank you again for your time, and we'll get on to the next problem.